Good morning, dear students. Welcome to this session on pre-stressed concrete. We are talking about Unit 2 of your syllabus, wherein we are discussing stresses in tendons. That was the topic it's taken up. Uh, we are into this session. A few sessions also have been done on this, like why to talk about the stresses in tendons, right? We have calculated the stresses in steels for two different cases where bonded tendons and unbonded tendons are being taken up, right? So, going a bit elaborated, this picture will show you how the bonded and unbonded nature of tendons with the beam having bonded tendons and unbonded tendons behavior. Okay, so just little bit analysis. So this picture, if you see, uh, there is a simply supported beam, okay, with a tendon where it is bonded type of tendon, and it is having some uh, load on it, a UDL. Okay, so this is a bonded beam we call, and let us see this picture where you have a duct. You have a duct provided where the tendon is inserted and anchored at the ends. Okay, so these are the anchors. Okay, and there is no connection between the concrete and the tendon. So they are not in contact. So that is why this is unbonded beam. Okay, right. So these two we are now going to uh, check it up according to the stresses in tendons, right? So x-axis we have load on the beam, okay, and the loads are like we have put it in terms of four category. So when you have just self weight of the beam, that is what we call at transfer. Okay, when uh, when you say the stress is transferred from tendon to the concrete, we call that stage as a transfer stage at transfer. Okay, then we have a stage called having loads, I mean member is in service, so we call this stage as service stage, at service. Okay, so at transfer and then at service, where the beam is placed in position in a structure and it is taking the loads, service loads, right? Then we have a stage called cracking load. If the loads are going to increase and it reach where you observe the visual cracks in the concrete, okay, then you still increase the load, the maximum capacity that the beam can handle before it fails, we say ultimate load. Okay, so these are the stages that we are going to check for the behavior of the stresses in tendon. So y axis is like stresses in tendons. Okay, so effective stress and initial stress and ultimate stress, okay, is being taken up for discussion. Say if you start with the uh, transfer stage, at transfer stage, this one is the point. So till that the effective stress is same in both the members, like both bonded and unbonded member will behave in the same way. So there won't be any stress. Effective stress is same in both the cases. And even if you see, if you take initial stress, where the stress at transfer very slight, I mean, we have worked out a problem also. So it is having just 1%, 1.2% of variation between bonded and unbonded beams. Okay, so very slight variation. So that is a behavior till the self weight of the beam is acting, right? Which means at transfer. Right. Once it crossed the transfer stage, once the pre-stress is transferred to the concrete, then it starts taking the loads. As load increases and reach the service load stage, you can clearly see that the bonded beams are taking more stress than the unbonded beams. Okay, the upper dotted line is bonded beams. Okay, so stress in steel is more in bonded beams than unbonded beams. Okay, then if you go to cracking load stage, so till that the behavior is same. Okay, so bonded beams are having more stress than the unbonded beams. Once the cracking stage starts, and then till reaching ultimate load case, there is a large gap of values between bonded and unbonded beams. So bonded beams are having very high stresses in steel than the unbonded beams. Okay, so this is a behavior of bonded and unbonded beam. It's clearly showing that bonded beam is having higher stresses in steel than the unbonded beams. And also the stage of loading, as it suggests that once the transfer stage crossed, then it is going to have working load stage, then cracking loads, then the ultimate till ultimate load stage. Always you see the difference between the stress in steel in bonded and unbonded beams are going on increasing. Okay, as the load increases, it is going on increase. I mean, the gap is increasing. Okay, so that is how the statement here, you see, bonded beams are preferable due to their higher flexural strength and predictable deformation characteristics. Okay, so this is the where bonded beams, rate of increase of stress is larger in case of bonded beams than unbonded beams. Okay, both in pre-cracking and post-cracking stages. So this statement is clearly observed with the diagram. Okay, the rate of increase of stress is larger in case of bonded beams than in unbonded beams, both in pre-cracking, pre-cracking in the sense this stage, post-cracking means this one. So both in pre-cracking and post-cracking, in both the cases, the bonded beams are having higher stresses, and rate of increase also is going on increasing. The gap is also increasing. So rate is also, that means the rate of stress increase is increasing, right? So that is what we can say about this diagram. Okay, so just to compare how stress in steel uh, is having variation in case of bonded and unbonded beams, as the loads increase from 0 to the ultimate load. Okay, so that is what we observe in this diagram. And this picture is to talk about the other statement that we gave, that the bonded beams are preferable due to their predictable deformation characteristics. This one, predictable deformation characteristics. So bonded beams cracking pattern is very regular and is predictable. This pattern we observe in case of, where the tensile stresses uh, crosses the cracking value of the mean fracture value of the concrete. Okay, limit of fracture. Right. So that is a behavior of bonded beam. Whereas when you see the unbonded beam, the cracking behavior is vague behavior, where the cracks are now propagating in a bizarre manner, where you can't predict how this crack is going to progress. Okay, this is a very regular behavior where bonded beams will behave, right? Whereas unbonded beams, the cracking nature is completely unpredictable. Okay. Okay. So that is a problem with the unbonded beam. Okay. So bonded beams are preferable when you know talk about higher flexural strength and deformation characteristics. Means what? Uh, at least you shall have pretensioned members, or you anyhow pretension members have limited application. So we go for post tensioning members, post tension members. So always grouting is preferable, so that it makes the uh, beam as bonded beam. Okay, so post tensioning grouted members are preferable. Okay, right. So just to see an example problem with how the stresses when the bonded and unbonded nature is involved. A pre-stressed concrete beam 200 mm wide by 300 mm deep supports live load 2.56 kilonewton per meter over an effective span of 10 meters. The tendons are housed in a duct, are located at an eccentricity 100 mm. Calculate the increase in steel stress due to the loading when the ducts are grouted, so that the strains in steel and adjacent concrete are equal. Means that it is in the other way, there is a perfect bond between the concrete and steel. Point A says the strains are same in steel and concrete at the level of steel. Meaning is that there is a perfect bond available. The ducts are ungrouted, so that tendons can move in the ducts without friction. Means there is no grouting, so it is unbonded. Okay, so category B is unbonded, right? Okay, so let us see the data. Young's modulus of steel, take a value, it is not given, and Young's modulus of concrete, assume some data if you are not having the data. So 35 megapascal, grade of 35 concrete, and 35. Gamma of concrete is a standard number, maybe symbol gamma or D can be used, density. So 24 kilonewton per meter cube. So estimate modular ratio ES by EC value, that is coming around 6. Self weight of the beam is like the cross section of the beam given, 200 by 300 cross section it is. Okay, so this is like 200 mm, this is 300. Where the tendons are placed, 100 mm eccentricity. I mean, this location, this is the location of the duct provided. Okay, 100 mm is the eccentricity. 150 is the distance of the bottom fiber from CG line, so it is 100. Okay, then what we see here is live load on the beam, which is 2.56, which is already given to you. The total load on the beam is going to be summation of 1.44 and 2.56. So it makes 4 kilonewton per meter. So second moment of area, BHQ by 12, which can be 45 into 10 power 7. It is just a typographical error. So 45 into 10 power 7 mm power 4. Correction from the textbook. Bending moment at the center, WL square by 8. Span is given 10 meters. W means total load. Use total load value for L square. Divide by 8 becomes 0.125. So which comes around 50 kilonewton meter is the bending moment at center. Okay. Now if you take a case of bonded beam, what is the stress in concrete? M y by I, right? So bending moment is 50 into 10 power 6. Y means the distance of the location where you want the stress. Where you want the stress at the level of steel. Where is the steel? 100 mm from the CG line. That is this 100. Okay. Right. Don't go for putting the y value as 150. We are not calculating stress at the bottom fiber. That is a different case. Okay. When you want to know calculate the resultant stress in the cross section of the concrete, then we will be substituting the top and bottom fibers. Now we are concentrating or we are calculating stresses in steel, so that's why we want stress in concrete where steel is there, right? So 100 mm is the distance, and I value 45 into 10 power 7 is giving you 11.1 Newton per mm square is the stress in concrete. Now if you want stress in steel value, modular ratio into stress in concrete. This formula we have discussed when we talk about these bonded and unbonded beam category, right? So that is in the previous session we have talked about this. So you can see alpha into F is the stress in concrete at the level of steel. Okay, so that is this one, and that is coming around 66.6 Newton per mm square is the stress in steel. Okay, now unbonded beam. So stress in steel is like straight away formula which is being derived in the last session. So alpha y w total load L square by 12 I. So alpha modular ratio 6 ES by EC value. Y location of steel from CG of concrete, and WD, that means total load is 4 L square. L is 10 meters converted into mm square. 12 times I value 45 into 10 power 7. So this is 44.4 Newton per mm square. So for the same beam with same tendons, everything same, you can see the bonded beam is having higher value of stress in steel, whereas For unbonded beam, it is 44.4 only. Okay, this is also mathematically also we have proved whatever is the behavior which is presented as a diagram. Okay, right. So bonded beams possess higher stress in steel than unbonded beams. Right. So that's all about the uh, stresses in tendons. The next session we'll talk about cracking moment and the last topic of this unit. Okay.